may achieve the high spin-Chern number state in the framework of the feature spectrum topology. If we follow the typical process that calculate, topological invariant number calculated from the Bloch wave function, we may not see this behavior. And this prediction may be realized in a multilayer BI4 BR4, this system. BR4 BR4 is a quasi one-dimensional system, so it is relatively simple to control number of layers in experiments. And we find that in BI4 BR4, the behavior of the spin-Chern number as well as the Z2 index are the same as a monolayer Campbell model. And this high spin-Chern number state will also be reflected in the spin-Hall connectivity. We find that the plateau of the value of spin-Hall connectivity is almost quantized, and the quantization increase as number of layers. And this high spin-Chern number state must be understood from the spin-Chern number that calculated from the feature spectrum topology. Because if we follow the typical process, calculate the Z2 index, the topological invariant number, we found it's oscillate, not increase linearly. And in addition, the BI4 BR4 shows a clear feature energy duality. So for example, for the monolayer case, the topological boundary state is gapless in the band structure, while the feature spectrum shows a gap. So number of gapless boundary state, one from the band structure and 0 from the feature spectrum, totally equals 1, which is consist with its spin-Chern number. And for the bilayer case, we observe one pair of gapless boundary state in the feature spectrum, but the band structure shows a gap. So 2 plus 0 equals 2, again, consists with its spin-Chern number. And in the final case, the tri-layer case, its topological boundary state in the band structure consists of one gapless boundary state and 2 gapped boundary states. And because its spin-Chern number equals 3, so we observe one pair of gapless boundary state in the feature spectrum. So total number of gapless boundary state in tri-layer case, 1 from the band structure and 2 from the feature spectrum, totally equals 3, again, consists with its spin-Chern number. So it's clear shows the feature energy duality in real materials. Okay, the summary of this talk. Our study shows that the spin-Chern number can always be well defined through the feature spectrum topology, even if we include the symmetry-breaking Chern in the Hamiltonian. And we identify the feature energy duality. Therefore, the bulk boundary correspondence still valid. For the material realization, we propose that the monolayer BI4 BR4 is a promising candidate to investigate the feature spectrum topology. And I thank all collaborators, especially thank my master student. He done all the calculation and wrote the manuscript. And I thank Professor Xinling from the Sinica and his former student, Yichun. They thank them provide a very useful discussion and share the original idea of the feature spectrum topology to us. And thank you very much.
So, thank you very much.